to PSCAD tutorial. This is the second part of building a simple power system network. So first point is replace RX line impedance with transmission line. In this model, this R and L is a equivalent transmission line, you can say, but there are transmission line available in PSCAD master library, so we will just replace these things, because in fault analysis you cannot mention the fault length from here. Okay, so you have to insert a transmission line. So go to master library. So this is the transmission line. So just take, you can take this, you can take this transmission line. Okay, just right click on it and copy it and paste it here. Okay, double click these things. For India, this is 50 hertz frequency, and say this is transmission line 1, and go to edit. Edit whatever in this uh, in this window, just select all and delete it first. Okay, nothing is here. Now go to master library again and copy these things. Manual, you can change the impedance manually. These things and these things. Go to edit, paste it. This is a standard model of transmission line. Go to master library again, manual entry of Y and Z, copy it and paste it here. Okay, so these are the values by default, but you have to change. I am taking R, XL and XC in ohm. Then I have to just fill these things. I am giving the values, so which are standard. This is 0.03293 10 to the power minus 3 ohm per meter. This is positive sequence resistance. This is 0.327 into 10 to the power minus 3 ohm per meter for positive sequence inductive reactance, and capacitive reactance. This is 280.1 mega ohm meter. This is positive sequence capacitive reactance. Actually, this is capacitive reactance of parallel capacitor. Okay, so in zero sequence resistance, this will be 0.2567 into 10 to the power minus 3 ohm per meter. For zero sequence inductive reactance, this will be 1.174 into 10 to the power minus 3 ohm per meter, and this zero sequence capacitive reactance will be 461.2546 mega ohm meter. So these are the standard value for 230 kV or 400 kV transmission line. Okay, now you can just change the length from here. It is by default given 100 kilometer. Okay, just replace it place it. Now connect the transmission line here. So this is now our transmission line. Okay, now first point is complete. Now use a bus bar. Where we will found, go to master library and bus bar. In passive element you can find this bus bar. Okay, just copy it and paste it here. Okay, so just connect the ammeter here. Just select it and press R to rotate and connect the bus bar here. Okay, double click it and write just B1 for bus. Okay, bus 1. Okay, okay, just okay, bus 1 here and connect the ammeter and bus 1 and this is our source. Just connect it with the bus. Okay, okay, now again copy the bus, just place it here and double click it. So this is bus 2 and connect the transmission and the bus 2 by this. Now connect the load resistance here. So this is the bus bar connection. So second point is completed. Now use a breaker and breaker logic. Where we will put a breaker just after multimeter, right? Just after multimeter. Go to master library and here breaker and faults. Go to there. Copy a 3-phase breaker and breaker logic. Okay. Okay. First we copy breaker logic. Just paste it here. Then go and copy the breaker and paste here. Okay, this arrow direction means power flow in this direction, so we have to just mirror the breaker. So just click on it and press M. So you can see the arrow direction is just reverse, so power flow from this direction to this direction. Now connect the breaker between the ammeter and transmission line and double click it. Okay, just give breaker name B1. Okay, B1 and go to configuration and display power flow. Yes, okay, you will see the power flow from here also as the multimeter. Now this breaker name is B1, so we have to change here also. This is B1. And breaker logic, what is the meaning of breaker logic? Now this is a one breaker operation, so make it one. So initial stage is close, and first breaker operation, and this is written 1 second, means the breaker will open after 1 second, but I don't want the breaker on unnecessarily, so make it 10, because our runtime of the model is 5. So taking first breaker operation in 10 second means the whole process will remain closed, as breaker will not open in between the runtime. Okay, now breaker is connected and breaker logic is mentioned. Now use of fault and fault logic. So fault, say this is a 100 kilometer transmission line, make a fault at 60 kilometer. So write the segment length as 60, and uh, you have to connect uh, transmission line again. So just what we'll have to do, just copy the rest of the power system, copy the rest of the power system and paste it here, and just copy it. Okay, so the remaining length will be 40, and this is transmission line 2, and parameters are as it is. And now connect this. Okay, so okay, so if we create a fault here, means fault after 60 kilometer, right? uh, so where we found the fault, go to master library. Here also, here the fault is there, so just copy it and go to power system. Now connect this fault here. Say the type of the fault here written is AG fault, so you can change from AG fault, you can change the fault resistance. I am taking fault resistance 10 ohm, and fault type is AG. You can change uh, by just make the B ES, so it will be ABG fault. Take ABG fault and change the fault logic, means time of applying fault, say after 2 second fault initiated, and duration of the fault say 1 second. Okay, so up to 3 second, uh, uh, after 3 second the fault will automatically cleared. So this is the logic of fault. Okay, so the fourth point is complete. Now run this model. Okay, let's see it is running correctly or not. Okay, now go to the arrow. Now you can see there is increase of current. Okay, the increase of current and power as well for fault. So if we magnify this portion, you can see two signals are increased. Those two signals must be A and B. So we, we are not able to identify the phases from here. So if we just click the IS, you will see the color code of the three components of IS. Three component means A phase, B phase and C phase. So and this blue is A phase, just make it bold. This is A phase and this is B phase means green, just make it bold. This is green. So by this way you can able to identify the different phases of IS and VS also you can find. Now there is another option, use of data tabs. You can just separate the different phases. How? Just connecting the data tab. This is the data tab. Okay, just make like this and connect this. This one index number one means first uh, first component of IS. So first component of IS is IA. Just copy it and paste it here and connect it here and like this. Now just double click it and make it 2 means second component of IS. This will be your B, IB, and double click it, make it 3 and this will be your IC. Okay, now just cut it and again add a overlay graph and just move the graph to top. Okay, now right click on it, go to graphs meter and control, add to curve, just paste. Okay, or and there is another way is just press control key in your keyboard and click on IB and just drag it here and left it, so you can see the IB is in the plot window. And like IB, just press the control key from your keyboard and press it here and drag it in the plot window and leave it. Okay, now if we run this and click on the arrow and make it a okay. So this is your IA is red and IB is blue, IB is green and IC is just blue. You can change the position of the various parameters by dragging it like this. Okay, so use of data tab is completed. Now FFT analysis to find phasor. For fault analysis, um, we need the phasor sometime because sinusoidal signal is not sufficient to analyze the fault. So we have to use FFT means fast Fourier transform. Just go to master library and go to CSMF and here you will find the FFT block. Just copy it and go to power system and paste it. Okay, FFT means fast Fourier transform. Now we are we want the phasor estimation for three phase uh, signals. um, we want positive sequence, negative sequence and zero sequence value. Just select it and make it 50 hertz. Number of harmonics is say 7. You can increase the number of harmonics as well, so no need of this. We want fundamental components of the phasors, so 7 is sufficient. The magnitude output is RMS. Okay, magnitude phase output unit is radian. You can make it as degree, but radian is good. uh, Anti-aliasing filter is okay. Frequency tracking, no need of this. And okay, press OK. So you can see the your three signal input here. You will have DC value. If we recall the Fourier transform formula, as Fourier transforms, some DC component are there, and the magnitude and the phases are there, right? So if we want to estimate the phasor of current signals, just copy it and paste it here. Just connect this. So IA, IB and IC is connected, and if we take magnitude here directly, I will have 7 components of each magnitude for positive sequence, negative sequence and zero sequence, as well as for phases of positive sequence, negative sequence and zero sequence. So we need to take the fundamental component of the magnitude and phases. So we need the first component. First component is always the fundamental component. So we again use the data tab. So just click on it, and like this you can rotate by pressing R and connect it here. So this will be your positive sequence fundamental magnitude. So just um, connect the output channel here. You will write IA. This is positive sequence magnitude, fundamental component means 1. Okay, make it yes. So this will be your kilo ampere. Okay, this is positive sequence current magnitude. Okay, just copy it, paste it, connect it here. This will be your negative sequence magnitude fundamental, and this will be your zero sequence magnitude fundamental. Okay, now you have to connect the phase also. So what will it? IA underscore, actually this is not IS underscore positive sequence phase fundamental 1. Okay, so this will not IA, this is IS. This all are IS, because we are finding the phasor of IS. Now you have to make it ES, and this will be your radian, say rad. So copy it and paste it and connect it here. So this will be our negative sequence phase fundamental. This will be our zero sequence phase fundamental. Okay, now if we want to plot the positive sequence magnitude and positive sequence phase, so just take a graph from here, right click it, add overlay graph to. So just right click on it, go to graph meters control, add to curve, just click on the plot window and paste curve. This is ISPM, and just right click on it, go to graph meters control, add to curve, right click on it, paste it. So this is our positive sequence magnitude for fundamental. This is fundamental positive sequence phase. So run it again. Okay, just click on the arrow. Now you can see the change due to fault of positive sequence magnitude is like this, and phase is this. So this way we can find the phasor by using FFT block. So point F is also completed. So this is the part 2 of building a simple power system network. Basically we are just analyzing the fault from this module. So this is end of this tutorial.